Oh, excuse me. All right. Then I will go through the original algorithm for the general chord type representation and mention some of its problems in order to propose a novel version of this algorithm. Finally, this new algorithm will be evaluated and will be seen in the context of harmonic analysis. So to begin with, representing harmony in a symphonic manner has been realized in multiple ways, depending on the musical era or idiom. These representations range from figured bass during the Baroque period and the Roman numerals to chord letter symbols found in jazz or pop lead sheets, and the pitch sets used for non-tonal music analysis, each being appropriate for the needs of its respective idiom, it being a performative use or analytical. Chris Hart tabulates the features of a systematic syntax of a good chord labeling scheme. Its encodings should be unambiguous, independent of context, able to be parsed by machines and legible by humans. And lastly, the system needs to be flexible to encode any possible simultaneity. He proposes his own syntax with all these characteristics. However, the suggested annotators need to be originally assigned by humans, which in turn is responsible for a factor of subjectivity. Recently, a tool was developed for representing chords independently of the idiom they belong to, namely the general chord type representation, or GCT for short. Utilizing a user-defined classification of intervallic consonants, it can automatically derive a root and a chord type from any given pitch subcollection. The aim of the study is to propose a new algorithm for GCT, one that handles more elegantly and more efficiently the issues that arise in the original version. These issues range from ambiguous outputs to untidy encodings of extensions and foreign chord notes, plus coarse classification of dissonance in intervals. To emphasize the significance of the latter, we argue about the complexity of the perception of dissonance. Consonance and dissonance perception depends on both sensory and cultural parameters. Properties like roughness, harmonicity, or masking are either ingrained in the auditory signal or of simultaneous, or they are related to the biology of the human ear. On the other hand, there are some filters of the listeners which vary depending on the familiarity of the musical stimulus, their musical expertise and sophistication, their own preference to consonance or dissonance, and some purely musical factors such as the nuances of a musical style. All these constitute the perception of consonance as a biocultural phenomenon. The multi-phased perception of consonance leads to classification of intervals that also varies throughout history and cultures. A series of studies have been conducted that aim to model intervallic consonance alongside the empirical research. However, all that collection of work does not conclude to a definite gradation of consonants in intervals. For instance, Hutchinson and Knopov organize intervals in this way we can see here. Most consonants unison, followed by perfect eighth, the octave, perfect fifth, fourth, major sixth, and so on. Meanwhile, Schwarz proposes this different organization. They differ at the degree of consonant of the minor sixth, the minor third, the tritone, the minor seventh. The most consonant and the most dissonant intervals are usually the same, the octave, the perfect fifth, and on the others in the minor second. It would be useful to apply this knowledge regarding the perception of consonants and intervals as building blocks of chords on a chord encoding scheme. Basic auditory principles such as the octave equivalence, the complementary interval perception, aspects of harmonic series, for example, the concept of root, compactness of a chord, it being written in a closed form, should be considered in a harmonic representation. The original GCT algorithm was designed to represent chords in a meaningful way in diverse musical idioms. It organizes pitches in a compact form and assigns the arrangement a root/pitch reference within a context of a key. Assuming a user-defined binary classification of intervallic consonants, henceforth a consonance vector, the system outputs a chord label specific to a given harmonic system. For example, tonal, whole tone, atonal, etc. To illustrate better how this operates, let us see the following example. In the key of G major, denoted by this integer list, and a consonance vector shown here, the thirds, the sixth, the perfect fourths and fifths are considered consonants. Let us consider the pitches 54, 60, 62, 69, and 74, which are F sharp, C, D, A, and D. These MIDI pitches are translated into the pitch classes 0 to 69. Then the algorithm searches for a subset of maximal length that contains only pairwise consonant tones. Here, the maximal consonant subset is 269. After that, it reorders the subsets in a compact form and transforms it into chord base 047 with root 2 here. The remaining pitch class 0 is appended on the right-hand side of the base as an extension 10. Therefore, we get the GCT representation 204710, which is the dominant seventh chord. And in the context of a G major scale, it becomes a chord bit on the fifth degree here. That is the seventh semitone of the scale. However, this algorithm often is undecided on multiple encodings due to the fact that the consonance vector is purely binary. For instance, a major sixth chord, 0479, and a minor seventh chord, 03710, are rated equally good. The number of such tied cases is relatively high. Therefore, additional disambiguation rules are required. Furthermore, the extensions are simply appended to the right of the chord base, which is an issue for higher cardinality chords. Other rules, like reordering the subset in a compact form, may be unnecessary. For these reasons, we currently propose a new version of the GCT algorithm. In this novel version, a graded consonance vector is allowed. Again, we will see how this works through an example. Using the pitches 5, 0, 3, 9 that are F, C, A, and D flat. The choice of the consonance vector will be discussed in a bit. For now, let us say that the most consonance intervals have the smallest values and the most distant the largest. Unison has the value 0 as the placeholder. At first, all possible intervals are checked and rated according to a given vector. In step 1, in this figure, each pitch is depicted as a node, and from there a tree is constructed. The bold lines are the ones with the smallest weight. Afterwards, for the most consonant ones, it considers all remaining pitches and picks the ones that is the most consonant compared to all its previous. In step 2, there are two weights added together, as you can see in the figure. Once more, the smallest one is chosen. This process iterates until there are no more remaining pitches. The most optimal path is through the pitches 5, 9, 0, and 3 in that order. In GCT notation, it becomes 5, 0, 7, 0, 4, 7, 10, which is an F dominant seventh chord. A graded consonance vector opens many testing possibilities. One could use values from empirical studies. Such a vector would greatly favor a perfect fifth. So in the output representation would resemble the harmonic series. The vector we previously used favors both the perfect fifth and the thirds. The complementary, which are the building blocks for standard triads. The complementary intervals are regarded as less consonant, the perfect fourth and the minor sixth, the minor and major sixth, while the remaining intervals in increasing dissonance are the tritone, the minor seventh, the major second, the major seventh, and the minor second. Apart from that, we can create a vector for atonal pitch collections. Under the principle that tonal music, that the intervals in atonal music are handled equally, we read all 6 interval classes with the smallest weight, 1, and the remaining 5 intervals have a value equal to 2. The novel version was evaluated on a list of common chords found in classical and jazz music. These chords were encoded in both versions of GCT, next to a representation as suggested by Hart's syntax. Here you can see the table. The complete one is, you can find it in the paper. These chords in both versions were encoded the same way, as you can see. In tetrads, the novel version shows a preference to major and minor triads for bass, and the stack of thirds principle emerges. Ambiguities, like the case of a minor 7th chord, are no longer appearing, especially at chords with 5 or more members. However, symmetric chords like a diminished 7th chord or sus2 or sus4 chords are inherently ambiguous and require contextual information to be confirmed, which still requires some additional rule-based decisions. Foreign notes like the suspended fourth and the dominant sus4 chord are successfully encoded. Root finding is also operating well in most cases, as you can see in this table. Furthermore, chord inversors are correctly identified in both versions. In the novel version, cases with tied outputs are dramatically reduced from 85 to 9%. Note that these ambiguities are resolved in a non-rule-based fashion. With respect to non-tonal representation, we tested for all possible TN types. TN types were reproduced at 81 success rate in the novel algorithm compared to 77 in the original. All trichords were correctly encoded, while only 2 out of 34 for tetrachords were inconsistent, 13 out of 16 for pentachords. In this section, we shall compare different encoding schemata by analyzing the reduction of the first 5 measures of Rhapsody in Blue. Here we see chord symbols, Roman numerals, the new GCT representations, and labels according to the Hardy syntax. We can observe that GCT manages to automatically annotate all chords, even the second one, in which all other systems fail. If we assume some root, it would be possible to annotate this specific chord with Hart's syntax. That means, though, that a human intervention is required. One advantage of Hart's is that it accounts for an harmonic spelling opposed to integer notation of GCT in reference to the key. In conclusion, we observe that ambiguous cases are significantly reduced. The need for additional external rules is decreased. The proposed scheme covers all features of a well-defined chord syntax, since it is illegible by using integer notation, and it is flexible to encode any pitch collection up to 12 pitches. It can automatically arrange pitches from bottom to top in decreasing consonants, and calculates a root. It successfully recognizes foreign notes, such as extensions, suspended notes, or added notes. In the future, we plan to further incorporate syntactic context to better assist automatic harmonic analysis and reduction. Finally, by extending the consonance vector, it could potentially encode microtonal simultaneities. These are my references for presentation. Thank you everyone for your attention. I'm eager to answer any potential questions.
Thank you. Thank you. That's a really interesting presentation. Are there any questions for Konstantinos?
Hi, can you hear me?
Yeah.
Yeah, I had a quick question. I wonder about this method. It seems to me in some cases that, so this is a possible challenge that comes to mind for me, that in some cases consonance and dissonance have to do with more than just the specific intervals. And the case that comes to mind is the augmented triad. And it's not because of the symmetry of the augmented triad, but the fact that major thirds are quite consonant. And somehow when you put two of them together, you get something that's quite dissonant. So I wonder, maybe for a test case where you're not dealing with just an augmented triad because you have the symmetry problem, but say augmented triad plus a major seventh or something like that, how would this method deal with that? And do you think it would be effective in dealing with that kind of chord structure?
Thank you for this interesting question. So it all depends on the consonance vector we suggest. If we indeed say that major thirds are consonant, then there would be an issue at such a symmetric chord. But if you had some parameter that, for example, you favor a fifth instead, you have an augmented triad plus a seventh. So there is a fifth between the third and the seventh note. So you could have some triad on the top three notes, and then you would add the one below that was originally the root. I think there is one in the table I showed you before. I don't have the augmented seventh. No, it's not there. But it purely depends on the vector. If we change the vector, it could solve such an ambiguity. Does this?
Yeah, thanks. That is that's a good point about that particular example. Yeah, thank you.
Other questions for Konstantinos? I have a question. How what do you see as the so you mentioned some sort of next steps that you're planning on taking. How do you see this being used? How do you see this being applicable to automatic analysis or analysis projects, or what do you see as the advantages of this system for those?
Having such a system, thank you for the question first. Having such a system makes the life of an analyst much easier because it can suggest an encoding, a potential chord label at certain spots, and make the life also easier for people that want to parse a lot of harmonic scores, symbolic musical sheets that need to be digitized and can be automatically analyzed. You don't have to go through everything manually. However, this has lots of problems because musical surface has many elements, and the system as it is currently just looks vertical slices. You have to account for metrical issues, for hierarchical relationships, and so on. So incorporating these details and that context will help producing a system of automatic harmonic analysis.
Could I add, I'm a co-author of the paper with Corpus. Just to add that this encoding tries to kind of maximize the reordering of pitches so that consonance is at the bottom, and then more dissonant things go further up in your list. And it has similarities, for example, with Pankat's virtual pitch finding algorithm. I don't know which know that, but that is biased for the major triad. In our system, you, as a user, define the vector consonant dissonance, and we know that consonant dissonance is culturally dependent. So you could do different things, and this is open. Interesting things is, first of all, that it gets very close to our encoding of tonal chords and the way we use encodings for tonal music. It also gets very close to pitch class set theory. And it also allows other things, like, for example, quartal harmony. You can say that perfect fourths are really good and minor sevenths, and then it will organize your harmony according to those intervals. Or if it's whole tone music, you can say major seconds are the most consonant in quotations, and then it will organize. The tonal system is a kind of instance of this representation, and also the pitch class set theory is another instance. And there are other possibilities which we haven't really explored. We can see how it can work with other things, and it has a potential, both theoretical of what a chord is in the end, and how this way it's sometimes better, for example, than the stack of thirds method. The example Jason mentioned, if you use stack of thirds, then of course at the bottom you will get the augmented triad because you just stack thirds. But if you have GCT, then the perfect fifth is not there, so it will not like it very much. It might prefer a different ordering of the pitches. Okay, sorry, that's it.
No, thank you. I see that Josh has his hand raised. Josh?
Hi, thanks for such an interesting and thought-provoking paper. I'm interested to kind of pick up on these same questions about the use cases in post-tonal or atonal, let's put that in square quotes, music. And like, would we need to develop kind of new vectors for each, I don't know, each body of work or each style that we're dealing with? I saw there was a brief mention of a vector that just treated all intervals up to the tritone as equivalent. I don't know, I'd just be interested to hear how you might go about applying this approach to post-tonal and non-tonal music. Thanks.
Thank you for the question. It's more of a coding problem, that since you have a system that can encode tonal triads on tonal chords in general, it's a subcategory, and then you have another subcategory that you can give any pitch collection, and it can make the TN type of that. So it's just possible, and you can use the same algorithm to encode uniformly and in the same fashion. What's on the paper, the notes and the pitches. It's basically doing pitch class set analysis. It's the same method, but we can see that it's a subcategory of maybe a broader scheme.
Excellent. Claire, I saw you had your hand up for a minute. Did you still have a question to ask?
Yes, I'm just worried about all the noise behind me, but hopefully you can't hear it. Yeah, it's. I'm actually curious about how. So first of all, I'm wondering if there's some kind of if the algorithms available that we might sort of test it out or play around with it a little bit. I'm really curious to actually use it. And then the other thing had to do with the kind of more practical aspect of using it for for anything. So if we think about that many of us have training in music theory, and kind of reading this notation is not terribly painful, but for a lot of other people it might be. So in terms of having an automatic system, it's I see that the main usage is for this sort of like automatic labeling, but at the same time, if we wanted to adopt this system, say I'm making a corpus, I want to include harmonic labels. Now, do I need like multiple harmonic representations? One, you talked at the beginning about Chris Hart's dissertation and the idea of machine readable and human readable. I'm wondering how you kind of tried to balance this in terms of the practical aspect of others using your algorithm.
Yeah, indeed, it's an issue. The thing, integers may be somewhat understandable by musicians and musical experts overall, but not very easy for the less experienced. It could be possible to adopt a similar idea like Hart's dissertation, to assign a label, a text label to chords or encodings for the most common ones at least. And then again, similarly, like the TN types, they also have a labeling. They have a code number like 426, etc. From Forte's list of pitch class sets. So it is possible and you also mentioned about the algorithm. At the moment, it's not uploaded in GitHub, but soon it will be publicly available.
Thank you.
I think covered everything as you mentioned.
Thank you, Konstantinos, for a very, very interesting talk.
Thank you very much.
I'll thank Konstantinos for that. Our second talk is being co-presented by Mark Gotham and Jason Just. Mark Gotham is a researcher at Saarland University, and Jason Just is Associate Professor of Music Theory at Boston University. Their talk is called Serial Analysis, a digital library of rows in the repertory and their properties with applications for teaching and research. Mark and Jason?
Thank you very much, Lee. Thank you all for coming. So I'll start by saying we're all sort of on the same page here, I think, in the sense that we all understand what digital libraries are, what they can be used for, and how they can be repurposed in all kinds of different ways. So we're all already past that point where collecting musical materials is only about, say, scores or audio sources or manuscripts or things like that. That's all incredibly valuable. But I think there's more understanding, at least in the musicology side, that that's something that we need to do, and less perhaps familiarity with the idea of gathering these kinds of digital libraries of human analyses particularly. And we've seen in this previous talk and at other points in the day, some of the insights into the recent work in that area and the things that you can do with that. Human analyses of various kinds, of all kinds of ways in which we might want to annotate a musical event or structure or score or form to record someone's view of what's going on in there. And we've seen some developments of that in recent years. Some really exciting things have been going on. Hart's work, others, again, that have been cited earlier on. Honestly, a lot of it has been centered on tonal harmonic analysis, though, I think it's fair to say. And it'd be great to see us broaden out a little bit into other kinds of musical repertoires and other kinds of musical parameters and annotation types. So our part is going to be about serial music. The next talk in this session is also in this kind of area, though admittedly we're still firmly in the kind of pitch space, at least for the present purposes. The other thing I think that's important to discuss and open up as a kind of motivator here is what links very nicely to this themed conference of bridging the gap. And I see that having many different meanings and important sort of significances for our field. What kinds of gaps might we bridge? Between repertoires, to be sure, between different people and groups of people and interest groups, I think is a key one. So you've heard from our title that we're not only about producing this resource for research, although that's clearly one of the emphases, but also for pedagogical purposes. That's a key emphasis of what we're about here. And indeed, prospectively, for more sort of public-facing outreach elements, insofar as serial music and tone rows, really have any kind of public-facing angle at all. Again, that's one of the reasons why there's sometimes more of an emphasis on tonal chord progressions, right? So with all of that's kind of percolating in the back of the minds, and this is also connected to a lot of other really important sort of moments in our time, sort of culturally, and certainly in music theory in terms of inclusivity and representativeness. And so, when we're building this corpus, we're also thinking about going beyond some of the more narrow repertoire constraints that have been looked at in the past, and again, trying to make it accessible to more people in more different ways. So tone rows, I present this as a kind of new and slightly different thing to be gathering as a digital library, though actually I should caveat that by saying that this is one of the elements that actually has a longer tradition than many of the other parts of our field. So there have been scholarly efforts since the 1980s to gather rows in the repertoire and encode them in a format that we can work with. And I also want to do a huge shout out for a Wikipedia page, which was one of the key motivators for me getting interested in this, where people just gathered together and put down rows that they'd come across. And that had, that's a variable quality and needed a lot of vetting when we started looking at that, but it's basically of a very high quality, basically very accurate, and basically replete with scholarly citations. So seeing that and seeing the collection of second Viennese school rows in previous scholarly work, I was really motivated to try and sort of bring this together, vet it all, and produce something that we could work with and develop. And when I saw Jason Yast's paper in Empirical Musicology Review last year, I just thought this is the time. I reached out to him, and the rest is history. So we'll tell you a little bit with the rest of this session about what we've produced so far in terms of a list and in terms of two applications. I'll tell you about applications on the more pedagogical end for anthologizing, and Jason will lead on the more researchy end of Fourier transforms and comparing relative tonalness of rows. So at this point, I'll share screen. So my face gets diminished in size, which is always good. Here we go to share here. And I'm going to just show you, basically introduce you to how we've gone about curating this. This is a nice place to start because it's simple, right? A CSV with composers, the work, the year approximate of publication or first performance, and then the row itemized in 12 columns. We've limited ourselves here to 12 tone rows, and we explain a bit more about that in the paper. So this is nice and simple. It's pretty, it goes a long way further than any previous resource. Dominic Argento is one of the many new composers that we have in here. Lots of Babbitt, of course, Berg, Boulez, Cage, Carter, Copeland, Dalla Piccola, Denisov. It's a larger range than you'll have seen anywhere before, and it's much bigger too, at about 650 examples. Now CSV, that's good for a sort of slightly more public-facing angle, and we'll return to that in just a second. But of course, you digital library experts will want to see a slightly better data structure than that. So we also have this JSON file, which goes a little bit further and includes a slightly richer amount of information for you to work with in your own work. Again, there's a site key, but a prime form. The original pitch, where that's significant, so all of the rows are given on pitch class 0 to start with, but sometimes the first pitch is recorded too. Composer, work, year of the work, and the source, crucially, where we got this from. Almost all of the entries here are from scholarly citable sources, and where they're not, we indicate that with just new and the person that we got it from. We want to thank Robert Morris for providing us with 50 rows of his own music, which is a fantastic new resource to have. He just had them lying around on his hard drive. So again, that's something that's now out in the world. And many other people, Laurel Parsons, many other people who are, again, credited in the paper. So we've got this, this JSON file, that's great too. But this, I wanted to draw everyone's attention to, again, the source is given in a kind of shorthand here, so page 2011 with a page number, that's fine. But if you want to do something automatic with this, then of course you need to know what that means. And so we also provide, not in the paper in like a PDF that you can't do anything with, but the a BBL file where these site keys are unpacked into their full reference form. So you could stick this straight into a new paper if you wanted to do something and build on this. Or else you can unpack them and export them in various ways too. So again, everything is sort of unpackable and repurposable, we hope. And if you see something that we should have done but didn't do, then I'm really interested to hear about that. Please let us know. Another crucial one you can see here is musical notation. So there is some code provided in here for taking the list as it is and unpacking it into musical notation, which of course is a whole lot more accessible for a lot of people than any of the formats that we've talked about so far. And that helps me to segue into this application, this more public facing element, where we have here as part of the Open Music Theory textbook, which I'm contributing to, not just the list of all the rows in a much more friendly public facing way, where you can search for a composer like Berg, or else remove that and search by year, or even by the 7th pitch in the collection, or whatever you like, those kinds of things. But also provide it in this musical notation here. And this is something that you can download or unpack in various ways. We could play it, but perhaps let's not. Annotated in various ways and organized, of course, alphabetically. I say, of course, alphabetically, but then the final element that I want to just draw everyone's attention to is a different way of organizing this list. So rather than just a data dump where you have these 650 rows, I've also provided some code for doing the basic kinds of transformations and property analysis where you can identify rows of a particular type. So here's a list of rows that are used more than once in more than one piece. So you can get to a sense of citation and how certain composers maybe cluster around particular rows. The all interval rows, of course, is an element that a lot of composers keep coming back to. Here are all of the ones that we found in the collection. Self-retrograde, and so it goes on, self-retrograde inversion, lots of different properties. The internal repetition of particular elements, so you know, discrete subsegments that keep recurring. And I don't know whether I'll be able to find it totally quickly, but one of the key ones that we included is rotation in the row, which we thought from having read previous work was a kind of rare property, and actually we found it's more common than that seems to be indicated by previous work. So this is a new kind of anthology about which much more could be said, where you don't just have a couple of potted examples of a particular device. That happens in the textbook chapter. And in the anthology, separately, you have this much larger list where people who are interested can kind of explore the wider way in which these things operate and how relatively rare they are, and also make some of their own kind of judgments about historical trends. Okay, thank you very much. That's enough from me. I'll pass over to Jason now to go on to the Fourier transforms.
Thanks, Mark. So I'm gonna show an application here. Am I, you all can hear me, I hope. Yeah, good. And let me just get, I have slides here, so I will bring those up. Okay, and we're all looking at my slides now, I hope. For an application of a use of this, I was very excited to have this huge database of rows now to look at with this tool. This is a method that I've used in a number of different ways. Other people have also in previous research, and it's particularly effective for talking about tone rows because of some of its mathematical features. I'll have to quickly kind of give you a Reader's Digest version of how this works. And there's a lot of resources to look up to get deeper into what's actually going on here mathematically. David Lewin is the first person to propose this. Ian Quinn was an important person in bringing its attention to music theory community in recent times, and myself, Emmanuel Amio, and other people have been doing a lot with this technique, the discrete Fourier transform on pitch class vectors in a lot of recent research. Roughly speaking, this is how it works. So we're dealing with pitch class sets here, and these are going to be segments of our row eventually, right? So, and the way we code these is as a vector. You just put a 1 in a place where a pitch class is present, a 0 if it's not present. What we're going to do then is take a Fourier transform of that, which converts that vector into periodic components. So something like this. So here's my C major triad, if that's my vector. And instead of looking at it as a collection of pitch classes, I'm going to look at it as a collection of periodic components. It happens that there are 6 of interest. Once we have those 6, we know basically what we're dealing with. And they divide the octave into 1 to 6 parts. Let's look at each of these individually. So why am I not advancing my slide? Okay. So the first one is going to tell us where the pitch classes are concentrated on the pitch class circle and how well they're concentrated on a pitch class circle. The second one divides the octave into 2. So it's going to tell us how the pitch classes are concentrated on a half cycle. In other words, a tritone cycle. And so this will be particularly large for tritones or things that are close to a tritone, like a 4th or 5th. When we go to the third, we're dividing the octave into 3 parts. We're going to get things that are triad-like. The highest value for that component is on a hexatonic scale. And the 4th is going to be particularly relevant for octatonic subsets. So we could refer to that as kind of the octatonic property of the pitch class set. The 5th is particularly interesting for tonal music because it gives us the concentration on a circle of fifths. So as you can imagine, that's typically very high for pitch class sets that you encounter in tonal music. And so when we're looking at tone rows, that will give us some indication of the tonalness of the row. And finally, the 6th one is going to balance the 2 whole tone collections against one another. So if something is a subset of a whole tone collection, it will have a very high value on that coefficient. The way we're going to use this, of course, Fourier transform gives us phase information and magnitude information. We're only interested in the magnitude information here. That's what I will call a spectrum. By the way, what we're doing the Fourier transform here on is a pitch class vector, right? So it's not the same thing as doing a Fourier transform on an audio signal. So that is a different domain than this one. We're looking at divisions of the octave, not divisions of a pitch continuum. So a spectrum will give us a magnitude value for each of one of these 6 components. A couple examples, if you were looking at diatonic scale, you get a very low value on the first coefficient because it's very spread out on the pitch class circle, but you get a very high value on the 5th because it's very concentrated on the circle of fifths. Let's say you're to take a major triad or a minor triad. Here you would still get a fairly high value on the 5th coefficient because it is fairly well concentrated on the circle of fifths, but you get the highest value on the 3rd because it's a triad, so it's very close to an augmented triad, which is kind of one of the set classes that maximizes that coefficient. So a couple interesting mathematical features of this, which are going to be important for our application, are that it's invariant under transposition. If we transpose the row, won't affect our results, right? It's also invariant under inversion. Again, invert the row, you get all the same results. Especially important here, it's also invariant under complementation. So this is the spectrum, right? The spectrum remains the same if I take the complement of a set, meaning I take all the pitch classes that are not present in that set. What that means is that if I take a segment of the row and I take the spectrum of that segment, if I were to take all the rest of the row, the ones I left out, I would get exactly the same result. So what we're going to do is divide the row into segments, and the spectrum will be the same for both of the segments that we divided into. Similarly, it's invariant under Z relation. What this is saying is that this DFT is giving us kind of the intervallic properties of the set. If the set has the same intervals, it will have the same spectrum. Okay, so here's how we deal with the data. So I'll give you an example, which is maybe one of the best known rows in our data set and also a very influential one, the one from the Webern piano variations. So here's our row represented in integer notation. And we're going to do 4 different ways of parsing this row. First, we're going to divide it into the main segmental hexachords. So we'll treat those as pitch class sets. And they happen to be both the same set class, the chromatic hexachord. In this case, it turns out to be a very common segmental hexachord, as you might expect. But we're going to do also another hexachordal partition that is oblique to that one. So it includes exactly 3 pitch classes from one hexachord and 3 from the other, so that those will not be statistically related to one another in any way. In this case, these are the hexachords we get for this particular row. We also looked at ways of doing this with tetrachord, octachord partitions. Again, because of this complementation property, I can just say this is characterized by the 0146 tetrachord. That happens to be one of the all interval tetrachords if you're keeping track. So the middle 4 pitch classes of Webern's row are an all interval tetrachord. To get one that overlaps that, I can take the middle octachord, or add together the 2 dyads at either end of the row. It just so happens that this is coincidental in this case, I think, that you get the other all interval tetrachord in this particular row. So what we'll do then is look at the spectra for all of those. And here's what this example would give us. For the initial and final hexachord, as you might expect, because it's a chromatic hexachord, you get a very high value for the first coefficient, very low for everything else. If I were instead to look at the middle 6 pitch classes, the highest coefficient would be the second. So in fact, we get kind of concentrations a tritone apart on the pitch class circle in that case. The tetrachords are pretty flat, almost flat spectra, because those are all interval tetrachords. So they representative of all different qualities. To get a contrasting example, here's another one. One of Babbitt's rows is characteristic of his rows, where he uses the hexatonic collection, meaning 013478. It's a highly symmetrical collection, and it is entirely characterized by the 3rd coefficient. So that's a very distinctive set class, which we do find happening pretty often in the segmental hexachords in our data set. Again, his inner hexachord has not a very high 3rd coefficient, but a high 2nd coefficient, meaning a lot of tritone related pitches in the middle of the row. And here are the tetrachords of that. One has a high 4th coefficient, one has a high 2nd coefficient. Oh yeah, so I had these animations in there. We don't need those. So I will show you just a few of our results. There's a lot of data here, and I would, if you're interested, I'd encourage you to look at the paper and you can peruse these results more closely. I'll just show what I think is particularly interesting in these results is how composers, the distinctiveness of different composers, and also trends across this whole data set, because we took every composer who wrote serial music, and obviously there's a lot of variety in that group of people in terms of the style of music they write. And the uses to which these tone rows are put. But we do find a lot of consistent things. So this particular graph is showing us composers who have non-random hexachords. So this is adding together those 2 hexachordal partitions. And where am I? Okay, so the first thing we see is that it's most composers tend to have in those hexachords a high first coefficient, meaning they tend to concentrate the pitch classes on the pitch class circle where they come close together, either at the beginning end of the row or in the middle. And on the other hand, in the higher numbered coefficients, because things tend not to be spread out, the values are typically low. Notice when I take composers that have their own significant results, almost all of them are significantly smaller than random on all of those, except for a couple instances. And one of the interesting ones is Berg. So this has been found before, that Berg's rows are uniquely tonal, and that tone, the idea of them being tonal can be described as they have relatively diatonic segments in them compared to other rows and also compared to random. And here we see that that is unique. He's the only composer of which that's the case. Every other composer has lower diatonicity in their row segments than would be expected for a random selection of rows, which is what that brown line is. Okay, for the tetrachords, here's that data. You might expect it to be similar than the other ones. I think where we find differences in this data with the hexachords, it has not to do with the difference between a tetrachord and a hexachord so much as it has to do with the fact that these two partitions are all inner outer contrasts, whereas the hexachord has the beginning ending contrast. And the one thing we see different is that a high second coefficient when we're looking at this inner outer contrasts and a low third coefficient. Because we find that also in the hexachord data when we compare the two partitions. So that's what this is. This is comparing the primary hexachord partition to the secondary one, the initial final versus the inner outer contrast. And some interesting things here are that the one thing that's consistent across composers is that the second component, again, this kind of tritone component, is always larger in the middle, not always, but typically larger in the middle hexachord versus the initial final. And one other interesting, there's a lot of composer specific stuff in this data. One very interesting one I think is Dalla Piccola, because his rows are often described as octatonic, and that is true, but it's not true for all partitions, as it turns out. We didn't find that he was particularly octatonic if you just took all the different partitions we looked at. But if you look just at the initial final hexachords, those are very octatonic. And so this is showing that if you contrast the initial final with the inner outer hexachords, you get like a much higher F4 in the inner outer hexachords. So that's just a few tidbits from that analysis. We could look at more if people have questions, though.
Thank you both. So questions for either Mark or Jason? Jason, what was the biggest surprise for you in doing this research? Like what results for what composer sort of made you go, oh, I hadn't thought about that?
That's a good question. Yeah. So there were a lot of things that weren't necessarily surprises. Some things that were that were kind of expected, but maybe not entirely expected. So having the high value on the first coefficient, low values in the fifth, it's kind of what I would have predicted. It's interesting how strong that result was, and how I think you can see in the data the influence of Webern's rows is very pervasive. I think that he has a particular pattern of the way his rows are constructed that is represented across. You could find other composers that you can identify them as kind of Webern composers, which not necessarily surprising, but not necessarily expected either. I think the one surprising thing was that Dalla Piccola stuff I showed. I expected the octatonicity to be high across the board, and it is only the hexachordal partition that emphasized the octatonic quality of those rows. Also kind of
chuck in, yeah, we were pretty surprised by that rotation property as well, right?
Right. Yeah. Yes. Yeah. If we're not talking about the DFT application, but yeah, I mean, I wrote something in Perspectives, in a Perspectives New Music article that said, like, you can't find this rotation property anywhere, meaning that if you rotate the row, you get the same row, right? So rotational invariance. And I only had one example of it, which is this Lutoslawski row, which is, it's questionable whether that's really a serial piece or not. But we were able to find a number of examples of it of different types. It's not a huge proportion of the data set, but I don't know if we looked at if it was statistically more likely than not. than you'd
That's
expect by
a good
chance.
point. So we had these comparisons of these properties against what we would expect from the random case in theory. So the paper reports on that, and also in a kind of quote unquote practice by chucking in a random collection of 200 or 300 rows to check, to sort of bootstrap ourselves and check that these properties were coming out about right for these random cases, and that any kind of deviation from that was kind of notable. So both on the sort of core properties of things that we teach about hexacaudal combinatoriality and stuff like that, and then also these Fourier transforms too.
Very cool. Mark, as you know, any pedagogical application of these things warms my cold, dead heart. And so I'm really curious about the collection that you have of composers reusing the same rows, or sort of rows that are used in multiple situations. And I'm wondering if you had any surprises about, oh, wow, this person is using the same row that this person did, or I didn't think that this row was used as much as it was, kind of thing.
Great, thanks. Yeah, great question. So the reuse thing was not so surprising to me, because it's pretty rare, and it was pretty sort of, in most cases, it was pretty linked to either a really significant property or a kind of homage. So the Ode to Napoleon, then it gets reused in later pieces that are explicitly using that, or explicitly referencing that same work, for instance. So there's a kind of historical dimension there, or a technical one. But yeah, these properties, I didn't really know what to expect, because it's the kind of thing that a music theory textbook will go through, like, this is what a hexacaudal combinatorial row looks like, and here's one example from Schoenberg, and typically it's always the same example that comes up for these things. So you don't really know, unless you're a really sort of immersed expert in this stuff, which I'm totally not. You don't really know how often you'd expect to see it cropping up, and I didn't know what to expect in those cases. So it was really just interesting to explore, and I hope that other people will continue to explore what's out there. And for me, as I said at the start, that's a key part for the pedagogical aspect too, is to not have these textbooks and anthologies where there are just like 2 or 3 canonical examples of a row property, or indeed a chromatic chord, the same Neapolitan 6th chords coming round and round every textbook. But to have a textbook with a couple of examples that you've chosen for a particular purpose. So again, in this case, I'm writing those chapters and picking out a few examples that I think are useful to sort of elucidate and exemplify. But then to also have this basically a data dump of other examples that people can explore freely. And in both of those cases, there's a huge, and we should sort of flag this up, there's a hugely subjective curatorial element on the analytical side. Sometimes it's really clear what the row is, but not often actually. And we've got a whole load of borderline, it's basically mostly borderline. What counts as a row? Does it have to be properly serially treated? Does it have to recur? Does it have to be stated near the beginning, melodically? And so all these questions. And the corpus, it really varies actually. And I think that's probably going to be one of the key questions for the sort of next phases, the next generation of this kind of research, is to, that the paper goes on to discuss that a little bit more, what we think might be important next.
Thank you so much. Claire, you have a quick question?
Yeah, some of the stuff you guys already touched on, but I was thinking when, Jason, when you said the comment about Della Piccola, and you were talking about this octatonicism that you found in the properties of the row, but then you made this sort of offhand comment like, oh, and these, sections of the row, or these sections of the partitions that you looked at, that you didn't really see any evidence of that. And it kind of made me think about the difference between the sort of propensity for the row, the affordances maybe of the row to sort of have these properties, and then what the composers actually do with them. And so, of course, some of the problems in doing this work is that a lot of the material is not out of copyright yet, so it's harder to kind of publicly digitize the actual works as opposed to the rows. But I'm wondering if you have some ideas for kind of connecting the analyses that you're doing from the rows with, the actual particular, what the composer did with that row, with a particular piece, kind of piggybacking off Lee's kind of asking about pedagogical resources. That's kind of what I was thinking.
Yeah, that's a really big question, and it's not a surprise.
Yeah, it was not a little question. Lee was like, "Do you have a small question?"
Just trying to keep us on time. Sorry.
I should be ready with an answer, because it's obviously a question that we thought about a lot too. So now, obviously just talking about the row that a composer uses, that's not necessarily talking about the music, because the way that these composers use their rows is highly variable. There's a lot of these rows that were, you get 12 rows from one piece because the composer has some kind of method of generating one row from another, and then using so there's not a single row for that piece. Very different from the standard Viennese, second Viennese methods that we usually think about. I think there could be a lot of approaches to extending this to talking about what happens in the actual music, and I don't know if I have a specific answer. Maybe Mark has more thoughts about it.
I think this is we're all sort of alighting on the same kind of research area, and I think in a nutshell what I would say is that we probably want to marry this up with some kind of automatic approach to segmenting up a score, right? So take a score, do some kind of automatic serial analysis of it to try and give some account of what rows are happening and where, which will be more or less easy depending on the case, of course, and that will bring all kinds of its own problems. And then align that with the analysis of those rows as they're happening, and somehow try to sort of turn the drum and give some kind of overview of what's happening overall as a sort of summary of that. And if you have only one row going round and round, like in some Krennic cases, then that's a particular kind of analysis that you can do. And if there's just this absolute, plethora of different things going on, then that's a different kind of analysis. But again, and I'd doff my cap to Brian Allegan here, who I had some useful conversations with, and reminded us that the analysis is not the archaeology, right? Once you've found the rows and said what's happening there, we need to sort of like draw on that, but get to something beyond it, to say really sort of meaningfully insightful analytical comments about serial music.
Sure.
Yeah, I would actually say.
Sorry, go ahead.
Okay, go ahead. There's kind of a converse to this also that comes to mind for me, which is that when Mark presented me with the project, that was my first thought was like, well, how much does the row tell you about what's actually going on in the music? And it actually, after looking at these, it actually becomes an interesting question, because you're looking at not exactly music per se, but what a composer likes to have as this pre-compositional material. You're looking at this kind of aspect of the compositional process, which in itself is kind of a different, but also an interesting question.
Yeah, absolutely. It is a really great project and a phenomenal amount of work. So thanks very much.
Yeah, thanks. Thank you both. Thanks, Jason and Mark for this wonderful presentation and for all of this work. Thank you.
Thank you.
Thanks.
And our third presenter is Joshua Balance. Joshua is a conductor, composer, and scholar currently researching for a doctorate at Christ Church, Oxford. His work uses a corpus study approach to assess patterns of harmonic practice in the music of Anton Webern. His talk today is called The Path to the New Note, Interval Distributions in the Music of Anton Webern. Josh?
Hi, thanks. I hope my slides are visible to you all. Firstly, I'd just like to thank everybody that's been involved in putting this fantastic conference on, and indeed to all of you for coming along and sticking with it all day for this final presentation this evening or this afternoon or this morning, depending where you are. I'm going to be talking, as my title suggests, about applying a computational approach to the analysis of intervals, which is a well-worn topic in the analysis of post-tonal music, and in particular in the music of Webern. But I would suggest that in the light of recent developments in the digital humanities and in computational musicology specifically, that there's potential for renewed and refreshing inquiry in this area. As is often the case, it's worth saying that this paper is merely a preliminary foray into this field, but I hope that it offers some early thoughts and some possibilities about what we can do. In terms of the scholarly background and the context for this paper, it's obvious, I think, that kind of traditional large-scale studies are hard and very time-intensive because they tend to require extensive manual work from the analyst, and then they hinge almost entirely on their knowledge and views, and this can make it difficult to carry out sustained work comparing large groups of music or indeed an overall style. There's some of these sorts of large-scale studies in the Webern literature. Alan Fort's The Atonal Music of Anton Webern covers the pre-serial atonal music, and Schreffler, her book discusses some of the transitional works, and Catherine Bailey's masterpiece, The 12-Note Music of Anton Webern, does what it says on the tin, really. It deals with the dodecaphonic music. So there's a little bit of overlap here, but not a huge amount. My research, this paper, and my research more broadly, by contrast, uses computational power to amass data and then to carry out what Franco Moretti has termed distant reading via statistical analysis. So this paper, as I mentioned, is about intervals, and as the title suggests, is particularly about interval distributions. And we can think of this as a representation of the proportion that each interval occupies of all the intervals in a movement. So how many semitones, how many perfect fifths, how many major sevenths, etc. And so the basic premise of this paper is to calculate an interval distribution for each movement in the corpus, and then I can compare these and compare them with regard to three particular research questions. The first is just to take a very kind of top-down view and ask, what are the overall trends in intervallic practice in Webern's music? And in particular, are all intervals used equally, or does he have particular preferences? There's something of a trope in the Webern literature to talk about the semitone as particularly Webernesque or kind of typical of his music, but there's rarely any evidence actually offered to support that assertion. And this paper, I hope, can go some way to interrogating whether that's actually the case. The second research question is then to consider how similar are the horizontal and vertical distributions in each movement. So when I said I was going to calculate a single distribution for each movement, what I really meant was I'll calculate two. One that deals with horizontal or melodic intervals, and a second that deals with vertical intervals, so the intervals between notes in a given simultaneity or verticality. And what we can do when we then have those two distributions is to ask how similar they are. If he prefers in a given movement to use lots of linear semitones, are there also lots of vertical semitones? This is a way really of trying to get at the question of harmonic integration, which was a topic of major concern for Webern and indeed for the other Second Viennese school composers. And so once we've established how similar are these distributions for a given movement, we can then apply the same questions about how that changes across time. And my third question, and this could not have been set up better by the previous talk, is to ask, and the questions that follows, what is the relationship between the interval distributions of the rows and the resulting dodecaphonic music? And I suggest, for me, I think this is almost the most exciting contribution of this paper, because it allows us to consider the effect of the row on the resulting music on a large scale, on a sustained level. So those are the research questions. I'm not going to spend an enormous amount of time on the methods. There's far more, as you can probably imagine, in the paper. I'll prioritize instead the results and the musical features, but I'll just do a kind of quick survey so that we're all on the same page and it's clear how this has come about. The first step was to compile the corpus, and this was relevant just for my doctoral research more broadly. So it involved encoding all these works as XML files so that I could then carry out further analysis with Music 21. And having done that, then to write the code that in very basic terms, the computer counts the intervals vertical and horizontal in each movement from that, it can compile an interval distribution for each movement, and then I can use statistics to ask questions of that data set. Just to clarify the corpus before we go any further, for my doctoral research, I've restricted the project to Webern's 31 works with opus numbers, so that takes us from the Passacaglia op 1 to the second cantata op 31. I consider each movement individually because they're all pretty harmonically self-dependent, and so that gives us an overall corpus of 107 movements. This obviously excludes the works without opus numbers and the early versions of some of the works that were later revised, but it gave me a corpus that crucially kind of spans several compositional periods: the tonal music, the three-tonal music, and the dodecaphonic music. There were a fairly large number of movements, and it kind of, I could condense it and I could still on my own encode it. It was still a viable amount of notes to put into Sibelius, even if that was a pretty time-consuming and boring endeavor. So we turn now to the vertical analysis first, and this is following probably what's quite standard practice now in computational musicology. But the first step is to create a harmonic reduction on one stave using the qualified tool in Music 21. So as you can see, these three bars get condensed down into this. From there, we then segment the successive verticalities and then record the duration and the intervallic content of each verticality before, from that, then compiling the total duration of each interval across the movement as a whole. It obviously throws up the question of in trichords or larger units, how I measure the intervals. I've opted to measure intervals from the base. There are lots of possible ways to do this. You could use the interval vector. In some of the music, it's appropriate to think about symmetrical constructions and measure intervals from the middle of a verticality. But inevitably, I needed an approach that would be just as relevant in the Passacaglia at the beginning of the corpus as to the second cantata at the end of the corpus. And at least to me, this felt like a viable, replicable approach, and one that at least on one level feels kind of an intuitive way to think about harmony, to measure these intervals and to hear these intervals from the bass. So that was the vertical approach. Turning to the linear, this was a bit more experimental because, at least to my knowledge, there's less of a kind of standardized practice yet in the field. But my first step was to create a melodic expansion for each movement, as you can see here, expanded from these four, or these three bars, 4 parts over to here. And what this produces is a representation of the music as a set of independent monophonic lines. Largely what we're trying to do is, if you have a verticality in an individual instrumental part, then it separates that out into 2 parts in the expansion, such that we get both approach intervals and both departure intervals. Obviously, these subsidiary parts then have an enormous quantity of rests in them, so as to avoid any duplication of other intervals. But that segmentation is largely carried out according to instrumentation anyway, and then according to the nearest note principles. So having done that, it's then all it's fairly common sense from there. You record the frequency of each linear interval in each of these parts, and from there we can then calculate the total frequency of each interval. So what we get is something that looks like this. This is plucked kind of at random the interval distribution for op 5 number 1. You can see in blue the vertical intervals and in orange the linear intervals. I'm not going to say an enormous amount about this distribution, other than that if all intervals were distributed evenly, we'd expect about 8% per interval. So you can see clearly here that there's quite a lot of variety, and that he prefers in this movement some intervals at the expense of others. So that was a whistle-stop tour through the method. So I'm going to turn now to the results and the discussion. And the first topic, the first research question, is to consider the overall tendencies across the corpus as a whole. So this chart is an interval distribution for the entire corpus, all 107 movements. Again, we've got for each interval vertical intervals on the left and linear on the right, and I'll discuss the colors in due course. It's worth saying that this is an enormously reductive move to compress this huge mass of music into this one chart, but also that this is exactly what's implied whenever we make offhand comments about, say, the semitone being typical of Webern's practice. It's just that the evidence isn't often there to support the claim. And so although this seems very reductive and very crude, that is kind of what we've been doing. So I think it's valid at least as a starting point. Again, we'd expect 8% per interval if they were equally distributed. So clearly there are some outliers. The only statistical anomaly we've got is the linear semitone, but it's worth saying that the semitone and the major seventh are generally more prominent. So that kind of confirms the typical view in the literature. We can also consider, though, those intervals that are particularly unusual. The linear perfect fifth, you can see there, is very rare, as are the vertical octave and the linear minor seventh. It's worth saying that the perfect fifth and the octave are clearly associated with tonal music, so it's perhaps unsurprising that they're used infrequently. As for the linear minor seventh, I don't know what that's about. Clearly he just didn't really like how that sounds. Turning to the colors, these are correlations, as you probably expected, with chronology. The more orange a bar, the more it increases across the corpus. The more blue, the more it decreases across the corpus from movement to movement. And there are 4 particularly prominent intervals here, all of which are linear. The octave unison and the tone become increasingly unpopular over time. And again, I'd suggest that's probably because of tonal connotations of these intervals. The minor sixth becomes more frequent. Again, I don't know what that's about. And the major seventh also becomes more frequent. And that's perhaps unsurprising. We think of that as a fairly dissonant interval, as discussed earlier. And so in a post-tonal aesthetic, perhaps that's not a huge surprise. The other overall pattern that I'm just going to spend a brief period of time on is the size of intervals. And this is picking up on an offhand remark from Pierre Boulez, where he suggests that Webern's intervals, and from the context we can assume he means melodic intervals, tend to get larger over time. What we've got on this chart are the correlations between the proportion of intervals in one octave span and corpus position. I'm sorry if that sounds a bit convoluted. Essentially, for each pair of bars, we've got the intervals in each octave span. So here, 0 to 11 semitones, 12 to 23 semitones, etc. And this is the correlation with corpus position. So if there's a high value, then intervals in this octave are becoming more common over time. A low value, they're becoming less common over time. We can see from this graph that Boulez's comment about melodic intervals is largely correct, but also that the reverse is true in the vertical domain. As a reminder, intervals here are being measured from the base, and so this perhaps suggests that verticalities are becoming more condensed over time, and perhaps, and this is speculation on my part, that the base is becoming less orally and textually stratified across the music. Turning now to harmonic similarity, we've got here the correlations between linear and vertical interval distributions for each movement, and they're ordered chronologically. A higher value indicates a greater degree of similarity, a lower value, a lesser degree of similarity. The mean is 0.2, which indicates a kind of general low level of similarity between these domains. And the correlation with corpus position is 0.3, which suggests a kind of gradual increase in similarity over time. The interesting thing, or the thing I really want to draw your attention to here, however, is that there's no major change around the onset of the dodecaphonic technique with Op 17. Instead, if there's any kind of big shift, it's much earlier around here with the move around Op 12 and Op 13 from the instrumental miniatures to the leader. And this is quite an interesting finding because it echoes my previous research on pitch class distributions, which also suggested that the onset of the dodecaphonic technique in Webern's music didn't create a major kind of rupture or stylistic disjuncture, but rather that if there was any major change, it happened earlier on. So it's interesting to see that same finding reflected now in interval content as well. And so finally, I'm going to spend the final proportion, or the final portion of this talk on the dodecaphonic music. And in particular, I'm going to ask, to what extent does the interval class distribution of the row predict that of the music? For anyone for whom pitch class set theory is just a dim and distant, but I'm sure very positive and enjoyable memory from an undergraduate analysis symposium. This is just a quick definitional reminder that interval classes treat inversionally similar intervals as identical. So a perfect fourth and a perfect fifth are both considered to be interval class 5, a semitone and a major seventh interval class 1. This is how intervals from a row are treated in dodecaphonic composition, and so how we can analyze them. So to ask this question, I ran an ordinary least squares regression analysis for the two interval class distributions of the row and the music. And in basic terms, what we get are these two coefficients. The p-values for all these regressions are under the 5% significance level. What this coefficient reflects is the percentage change in the music from an increase in the frequency of an interval in the row by 1. So if I add an extra semitone to the row, then we would expect in the linear domain an increase of slightly over 5% of semitones, and in the vertical of slightly over 7%. We might think, or at least intuitively, I did think of the dodecaphonic technique as sort of primarily contrapuntal. So it's a bit of a surprise to see that the effect in the vertical domain is similar, and in fact, even a bit higher than that in the linear domain. But this also poses the question of how topography comes into play. And this is topography is the way in which the rows are disposed. So it's how Webern actually then writes with rows in his music. And Catherine Bailey has identified two principal topographical strategies. The first, and this is what we might think of as kind of the archetypal serial technique, is block topography, quote, in which rows are set one after the other with all notes sounding in the order prescribed by the succession of rows. So there's one gradually unfolding chain of rows that controls the entire musical texture. The alternative is to use linear topography, in which, quote, several rows are progressing simultaneously in as many voices. So you can see here, the first movement of the symphony, we've got 4 different sets of row forms in the different colors, all unfolding simultaneously at once and cutting across different instrumental parts. So operating almost as a kind of background structure. So to ask to what extent topography might come into play, I ran further regressions on each subset of the corpus that uses block, linear, or combined topography. Intuitively, again, this is my kind of supposition, we might think that linear topography would have a greater effect on linear intervals and block topography would have a greater effect on vertical intervals. But either way, I would have expected that block topography would probably have a greater overall effect. In reality, as you can see from all these coefficients, it's all pretty similar. If anything, the strongest relationship is between vertical intervals and linear topography. But to draw this to a close, I think what this suggests is that the mechanical impact of the row on the construction of the music was actually limited. And from this and from the question of harmonic similarity before, we can propose or suggest that Webern achieved, whether consciously or subconsciously, essentially the same effect between the vertical and horizontal dimensions, irrespective of the constructive impact of the row. And so, finally, just a couple of concluding thoughts. The first, to suggest where this might go next, I'm particularly interested in intra-movement dispersion. So is he using particular intervals in to characterize structural sections of a given work, or are they used fairly evenly across movements? And then the other topic I'd like to look at concerns frozen intervals. So this is working on building on work by Janine Brown, which posits that in some works, Webern uses interval classes only in a specific intervallic context. So interval class 1 might appear only as a major seventh, not as a semitone or a minor ninth or anything else. And that we can now consider with this data set quite easily. So to broaden the scope, finally, what I hope this paper demonstrates is that we're now in a place where we can leverage computational power to assess stylistic practice on a large scale with empirical backing. Thank you.
Thank you, Joshua. That's a lot of work and really, really wonderful work. Are there questions for Josh? I'm of course interested in, you mentioned the intersection between the previous paper and this one. And so I'm interested in your thoughts on, I'm sure you were looking for Webern in their charts of, you know, the Fourier transforms, and how you think that that might line up with what your research is showing.
Yeah, I mean, it's like a dream to have these papers side by side. Yeah, I mean, I feel like we could just apply all the questions that were asked to the previous paper to this comparison between the set of rows that we have and that are in Music 21 as well, and to the corpus that I now have. I mean, it would be really interesting to compare, say, if we ran the Fourier transform on the rows and on the, I guess, distributions of the music, or even on the works themselves. I don't know. I'm slightly getting over my skis here, but I'm sure Jason has views. And then to compare those, it would be, it'd be really interesting to see the extent to which the properties of the row are then replicated in the music or not, and indeed whether that ties into any of these other variables: chronology, topography, instrumentation. Like, there's a big thing in Webern's music that I'm interested in like, how is the leader different to the instrumental music? Does that change over time? Does his vocal writing change over time? So any of these variables, I think, would be really interesting ways to think about these relationships.
Definitely.
Yeah, that's a totally doable. So you can do. I've done this actually with tonal music to look at distributions of pitch class sets in tonal music, but you can do a windowed analysis from what, you know, however you select to construct your windows over the course of the piece. You can derive some kind of weighted pitch class vector or pitch class multiset of some kind for each window of the piece, and then you can do statistics on those. And you could do that and then compare them to the rows and, like, say, look at different pieces with different types of rows and see if there's any kind of relationship between the windowed analysis and the qualities of the row. And the DFT would be a very effective tool for that, because it has this property of being a reversible transform. So, you know, once you've taken the DFT of all of those pitch class sets, you know, just as far as the pitch class sets or multi-sets goes, you are looking at everything, you know, every bit of information that those things can give you. It's all in there somewhere. So it's also a linear transform. So it has like this mathematical tractability that can be useful. You know that it's that it has all these linear properties.
We have a question in the chat. It's very surprising that linear 2, e.g. up 2, is overrepresented, but linear 10 down 2 is underrepresented. Is there a musical representation, or sorry, interpretation? For example, are down melodic movements done by leap rather than step, and could it be an artifact of your voicing procedure?
Yeah, interesting. I don't think down melodic movements done by leap rather than step. Yeah, I never considered changing or differences between direction of intervals, which I guess this starts to get at. But it would definitely be interesting to see how that differs. I don't think my voicing procedure, by which I assume you mean the way I did the melodic expansion, would necessarily come into play. I mean, that was pretty strictly just by instrumentation and then by nearest note principles to guide the voice leading. So I don't think that should be relevant. But I think what this more broadly suggests is that Webern thinks of intervals with the same interval class property as different and uses them in a different way, which is perhaps not that unsurprising if we think even just about like the nature of melodic writing or like performance, which was always so front of mind for him. Yeah, sorry, that's not that's just kind of speculation, but I'll think further about that. Thanks for the question.
other questions or thoughts for Joshua?
There's one thing I found pretty good. Claire, did you want to say something? Or
I was going to, but if you want to continue, I will step back. It was just a minor question.
There's one little thing that you in your results that looked particularly interesting to me, that you find the changes in the style happening not at the onset of serialism with Opus 17, but with the around Opus 11 or Opus 12, right? You attributed that to the from going from instrumental to leader as kind of the main genre. I've noticed in the Opus 12 pieces that, well, at least one of them starts off with an aggregate, or you might say a tone row, or an aggregate partition. So I wonder if you had any thoughts about this. I wonder if, maybe Opus 17 is not necessarily the beginning of serialism, but just the beginning of serialism as kind of a systematic procedure. Because of course these composers, Schoenberg and Webern, we're gradually starting to do this stuff, more and more, until it was actually fully formalized as some kind of technique. But that there might be something serial about the music before it becomes technically actually serial.
Yeah, totally. And I mean, a lot of Anne Schreffler's research has been and her book is looking at kind of proto-serial procedures in the earlier music. So there's a lot of support for that view. I mean, it's obviously the story that Schoenberg and Webern always told, was that the kind of road just gradually emerged out of this kind of gradual compositional experimentation. And although I think that the fashionable thing to do is usually to negate anything a composer says and critique it, I think in this case, as you kind of point to, there's quite a lot of support for it, and it makes quite a lot of sense. I mean, the thing that's just interesting for me is that you can see that significant change between Op 11 and Op 12. And you can see it, as I say, in this other paper, so in another feature of the music, and yet the move from there into the dodecaphonic music is so gradual. And I think it would be really fascinating to compare if somebody finds some money for some research assistants and gets more kind of Second Viennese works encoded. It would be fascinating to compare in, say, Schoenberg's music. Is the same true, that there's this gradual development into the dodecaphonic music, or when he begins using that technique, do we see a significant shift and change in his music? I don't know what the answer is, but it would be lovely to find out.
We've run a little bit over time, but that's because we had such wonderful conversation. So thank you everyone for sticking around for a few minutes. I gather that there is a social hour happening on GatherTown after this, so I'm sure that this conversation can be continued there. So thank you to our presenters. Thank you to Claire for putting all of this together. Thank you for inviting me to be part of it. I've learned a lot and enjoyed this very much. And thank you to everyone for coming and engaging with the material and asking questions.
Thanks, Lee. Thanks again to everyone for coming today. I know we tried our best to pick a range of times that worked for a very large number of time zones, which was not easy to do. And so some people are hungry and want to eat dinner, and I totally get that. And others of us might be fading because we got up too early. Just a reminder that we do have our fourth and final session tomorrow. That is now at UTC 1500 due to a programmatic error. We changed that a few days ago, and so that's been updated on the program. And that's our joint session with YAML. So we hope that everyone can join us there. And just again, final thank yous to everybody who made this conference possible today, and for all of your sustained attention and engaging questions. Thank you very much.
And since this is the last pure DLFM bit, I think everyone should please thank Claire for all the incredible hard work and imagination she's had to put into arranging them.
Thank you.
Thanks very much. I look forward to hopefully seeing you all again tomorrow. Have a good evening.